So here's another truss, and boy, does it look messy. You're probably thinking to yourself, oh my gosh, are we going to do this one? The thing that I want to show you here with this is that there are sometimes some tricks you can do that simplify your truss and make it a little bit less awkward to try to analyze. All right. So what we're going to do here, we are actually going to take a free body diagram first of the joint at G. Okay, yeah, it might look kind of weird to you, but we're going to take that joint at G and do a free body diagram of it real quick. And I'm going to show you something that's kind of cool. All right, so here's the joint at G, and if we look at that, at G, we might have some forces that are due to member AG or due to FG. Okay, so we'll put those on here. Call that TFG, and we'll call this TAG. All right, and then we'll have this other force that acts upward right here, and we'll call that TBG. All right. And without trying to figure out what the forces are, TAG or TFG, what I'm going to do is cut straight to summing forces here in the Y direction, where Y is upward. There we've got Y, here we've got X. We're going to go ahead and sum those forces in the Y direction. And when we do that, what we're going to find here is that we have TBG, and that's pretty much it. That's the only force we have that has a Y component. That's equal to 0. So we can say right away here that TBG is equal to 0. Once you find that out, what you can actually do is go in here and eliminate that member. You can go in here and say that member, it's like it's not even there because it doesn't have any force in it. All right. We can actually move on. We can do a similar thing over here at joint D. Think about doing a free body diagram there at joint D. All right, so we'll go ahead and do a free body diagram there. What we'll find is that we have a tension, let's say TDE, and we could have another tension that acts up like this that we could call TCD, and then we'll have another potential for a force going this way. We'll call that TDF. All right. I'm going to show you something kind of cool here. What we can do is we can define our coordinate system in a little bit different way than we're used to defining it. We can define it like this. Let's say that that's X and this is Y. If we define it that way, and then based on that coordinate system, we actually do a sum of forces then in the Y direction, what we will find is that just like above, the only force we have that acts in that Y direction that we've defined is TDF. And so when we sum these forces, that is going to have to be equal to 0. Okay? So there's another example of a member that can be eliminated. We can actually just cross that member right out, and it makes this truss a lot easier to analyze. There's actually one more in here that we can do kind of the same thing with. If we think about here the joint at H, think about that joint right there and do a free body diagram of it. What we'll have is a force, let's say here, we'll do it in the correct orientation there. We have this force HF, and we have a force acting up here of BH. All right, and then we have this other force that kind of acts up like this. And what I want to point out here is that it doesn't really matter that that force is not perpendicular right there. It's at this angle of 60 degrees. It doesn't really matter. This force FCH is the only force that has a component that lies along, let's say that's the Y direction there and that's the X. It's the only one that has a component that lies along that direction. And so we can make the statement that FCH is also equal to 0. So we have eliminated actually 3 members now. We just now finished eliminating FCH based on the fact that it's the only force here that has a Y component. And so if we sum forces then in the Y direction, we'll find that FCH has to be equal to 0. So we're going to eliminate that member also. So what I want to do is kind of codify what exactly we have learned from this. And what it'll do is enable us to look for these 0 force members, they're called. We'll be able to look for them and eliminate them from our truss first thing and make it easier to analyze. All right? So this is basically the rule that you look for. What you do is you find a joint with 3 members connected to it. All right, and what you do after that is you look and see if 2 of the members only 2 members are collinear, and there are no external forces, external loading or anything like that, acting at that joint. Then what we can say, the third member, the non-collinear one, is a 0 force member. All right, and after we figure out those 0 force members, what we can do is completely eliminate them from the truss, and it doesn't change how we analyze the truss. And I'll tell you what, in a few minutes here, I'm going to finish analyzing this truss after having removed those members. All right. Let me make one other comment here. Let's say that we had a truss that looked something like this. Let's say we had a truss that was built to where it looked, let's just say it looked just like this. Right? And we would support that simply, just like we've seen with some of these other ones. We have 2 reactions at that joint over at the left side and 1 reaction to the joint at the right side. Let me put some letters on here: A, B, C, D, E, and F. You think about here, which of these members are actually 0 force members? Well, what we can do is we can say, well, it's easy to use our rule that we just made up here to identify BF as a 0 force member and DF also as a 0 force member. But what's cool is, now that we've identified those 2 as 0 force members, we can remove them. Like I said, we can remove those from the truss, and it doesn't change how it gets analyzed. Well, now that we've done that, we can look at the joint at F, and based on looking at that joint at F, we can identify yet another 0 force member. We can eliminate that member right there, CF. And so after we've done that, we can totally eliminate that, and we end up with a truss that's actually incredibly simple. It's just a simple triangle with a single member that goes along the bottom. All right, what you can do actually here is you can just ignore that there were ever joints at those locations and just treat that truss just like that. So that's another nice thing that you can do when you're looking for 0 force members. I just wanted to correct one little thing here before we move on with the analysis of the truss that I started in the last couple of videos here. I had intended to put a force that acted downward up here, some kind of a force that acted downward on that truss, and I neglected to do that. This is that truss that we had eliminated these members from, and I just had intended to do that, and I forgot. So kind of mark that down if you're taking notes. All right, so that's just kind of a side thing there. All right, what I want to do now is we're going to go down here and notice that I have actually erased those members when I went down here and made a free body diagram out of the physical scenario that I started out with. All right, I've erased member BG, member DF, and member CH. All those have been erased now, and they're gone. What we can actually do here is, furthermore, we can just kind of erase those letters even, because we don't really care that there were ever joints there. It doesn't change how this truss gets analyzed. So doing the same process that we started out with, we've got this free body diagram here. We need to, first thing, solve for the external reactions, which are REY over here, RAY, and actually RAX turns out to be 0 because we don't have any external loads on here that would cause a reaction there at A in the X direction, so we can just eliminate that. That won't always be the case, but it is for some of these, and actually it is for quite a few of them, if all you have is vertical loading on your truss. All right, so what we need to do is we need to take this free body diagram and start off by summing moments. And I'm going to sum moments here about A, taking counterclockwise to be positive. And if we do this, what we'll find out here is that we've got a 2 kilonewton force that acts downward there at B, and that tends to create a clockwise moment, so we'll say minus 2 kilonewtons, and then multiply that by its perpendicular distance away from point A, which is just 4 meters. Okay, and then the next part of that is taking the 1.75 kilonewton force, and it also creates a clockwise rotation about point A. So we'll take 1.75 kilonewtons times, and it's acting at 8 meters away from point A. And then finally, the last force we have that would create a moment about point A would be the reaction at E in the Y direction. And that tends to rotate it counterclockwise, so we'll say plus REY, and it acts at a distance of 4 plus 4 is 8, and plus 3 there is 11 meters away from point A. All that stuff, you sum it all up, and it's equal to 0. So after doing that, what we'll find is that REY is just equal to 2 kilonewtons times 4 meters plus 1.75 kilonewtons times 8 meters. All that divided by this 11 meters. After doing that, we'll find that REY is just equal to 2 kilonewtons. Okay. All right, so we've got that's equal to 2 kilonewtons. The next thing we can do is sum forces in the Y direction, taking upward to be positive. When we do that, we'll look at all the different forces that act in the Y direction. First of all, we have REY, which again was 2 kilonewtons, so I'll put that in here, 2 kilonewtons, minus 1.75 kilonewtons. All right, and then minus another 2 kilonewtons. That's this force up here. All right, and then we'll take that and add RAY. All right, and set all that equal to 0. And after having done that, what we'll find here is that RAY is just equal to 1.75 kilonewtons. Okay, and so there we have found the reactions for that truss. Continuing on with our analysis of the truss that we started in the last couple of videos, what we're going to do here is we're going to start again by doing a free body diagram of a joint where we don't have too many unknowns. And so what I'm planning on doing here is starting with the joint at E and going ahead and doing a free body diagram of that and continuing from there to then find the other forces that are in the truss. All right, so drawing a diagram here of the joint at E, what we'll see is there's the joint, all right, and at that joint we are going to have this force of 2 kilonewtons. That's our reaction force that happens on that joint. We also would have, we're going to assume a tension again here. We're going to assume a tension in EF, so we'll call that TEF. And then we're going to put assume a tension also in this member that goes up right there, and that is member CE. All right, so we're going to assume a tension in that also. To make this free body diagram complete, we're going to put in some coordinate axes. There's X and there's Y. All right, and then finally we need to put in something that we knew about this. We know that it goes over 3 and up 4. That means again that is 5. And from that, it's fairly simple for us to go ahead and do the equilibrium equations off of that free body diagram. We'll sum forces first in the x direction, I guess, where we got rightward positive. And based on this, we've got minus TEF minus TCE times, and we just need the horizontal component, so we'll multiply that by 3 over the hypotenuse 5. And those are the only forces we've got with horizontal components. So we'll set that equal to 0. We can't solve that because it's got 2 different variables in it, and we only have one equation so far. So we'll go on to the next equation that we can write here, and sum forces in the y direction. And we sum forces in the y direction. What we'll have here is 2 kilonewtons acting upward plus TCE times, and we just want the vertical component, so we'll take that ratio of 4 over 5 to get the vertical component of that force. And those are the only 2 that have vertical components, so we'll set those equal to 0. And from there we can solve for TCE. Doing that, TCE is actually equal to 2 kilonewtons times 5 divided by 4. Doing that, it ends up giving us 2.5 kilonewtons. Okay, so that's good. From there we can take our, that's negative 2.5 kilonewtons. From there we can take that negative 2.5 kilonewtons and plug it back into this equation up here. And when we do that, we'll find that TEF is equal to, we'll say that that's equal to negative a negative 2.5 kilonewtons times 3 over 5. All right, and doing that, this ends up giving us here 1.5 kilonewtons. Okay, so there we've got 2 of our tensions that we were looking for. So that's it that we need to do for the first free body diagram. So what we've done so far is figured out the force here that is in member CE was what we did first. So we figured out that force in that member first, and then we from there we found the force that was in member EF. So now what we're going to do is move on to the joint at C. All right, so drawing the free body diagram of that joint down here. There's C, and we'll look at all the forces that act at C. All right. First of all, we have that 1.75 kilonewton force that acts downward right there on C, so we already know that one. We're going to assume a tension force here for member BC, so TBC. Then we're going to assume again a tension. Well, of course we already drew that arrow in there, but we assumed a tension the first time, so we have to assume that again. Pardon me, we haven't drawn that one in yet. That's CF, so we haven't gotten there yet. So that's TCF. We'll put that in there. And then we've got another one here that is let's see, that's TCE. Okay, and we've already sort of figured out the direction that that one goes. For a run here of 3, it has a rise of 4. So we'll put that in there, and that's 5 there. To complete this out, again, it's usually a good idea to put in some coordinate axes. So there's X, and here's Y. All right, and based on that free body diagram, we can now write some equations. All right, so looks to me like if we write the equation that is in, let's say, the horizontal direction first, summing forces in the x. That'd be a good thing for us to do. So there we've got minus TBC, all right, plus TCE, and TCE is actually a negative 2.5 kilonewtons, so we'll put that in here, minus 2.5 kilonewtons. And but we only need just the horizontal component for this equation, so we'll take that and multiply it by 3 divided by 5. All right, those are the only two forces we have that have horizontal components. So we will go ahead and set that equation equal to 0, and from there we can solve for TBC. TBC, based on that equation, actually ends up being 1.5 kilonewtons, or actually negative 1.5 kilonewtons. All right. From there we can move on and do an equation for the y direction, the vertical direction there. Take upward to be positive. And there what we've got is we have this 1.75 kilonewton force right there. 1.75 kilonewtons. It acts downward, so we got to put a negative sign in front of that. We also have TCF, so minus TCF. All right. And then finally we have just the vertical component of TCE. So we'll say minus TCE. Again, TCE is a minus 2.5 kilonewtons. All right, but we just want the vertical component, so we will take that value of TCE and multiply it by 4 over 5 and set that whole thing equal to 0. Having done that, we will actually find that TCF, this value we're looking for there, is simply equal to 0.25 kilonewtons. All right, and so that's basically it. We've gotten two more values here. We know that this is 1.5, negative 1.5 kilonewtons, which means it's in compression, and this one is 0.25 kilonewtons. That's positive, so that one will be in tension. So let me go ahead and sketch those in here. Now we have found that one and that one. Moving on, we can now find, we need to do a free body diagram of the joint at F, and what that will allow us to do is to find the forces that are in BF as well as in AF. All right, so here is the joint, let me do that in black. Here's the joint at F. All right, and now we'll look at all the forces that act on that joint. We have this force FE that goes to the right. We actually found out, or force in EF, it's TEF, and this is actually equal to 1.5 kilonewtons. All right. We also have a, we'll call this force up here, this is TCF. All right. And that here is equal to 0.25 kilonewtons. All right, so those are two forces that we have on that joint at F. Now we have these other ones that we don't know yet. We have a tension here, TAF, as well as we'll call this TBF. It goes up like this. All right, so there's what we've got there. Let me, as always, try to do good practice here. This vector right here has a rise of run and a rise and run both of 4, and so if that's the case, then this right here is actually going to be the square root of 4 squared plus 4 squared, that would actually be the square root of 32, and the square root of 32 is approximately 5.657. All right, so that's what that hypotenuse is there approximately. All right, and so now that we've got all that stuff, we're going to go over here and do some equations on this. The thing to notice here is that we have these two forces, TBF and TCF, acting in this vertical direction, and we actually we know TCF, we don't know TBF. If we do the vertical direction first, all right, summing forces in the y, then what we'll find is that we'll only have one unknown variable in that equation. All right, so here we'll do that. We have here 0.25 kilonewtons acting in the positive y direction plus TBF, and then we just need the vertical component of that, so we'll multiply by 4 divided by that square root that we just found, which is approximately 5.657, and all that's equal to 0. So doing that calculation there, we'll find that TBF turns out to be negative 0.354 kilonewtons. Okay, so that's good. Next we can do the sum of forces in the x direction, where rightward is positive. And here we'll find that we've got TEF that acts to the right, so that again would be 1.5 kilonewtons. Here we have minus TAF, all right, minus, we just need the horizontal component of TBF, so we'll put that in there, TBF, and just the horizontal component, we multiply by 4 divided by that hypotenuse, 5.657. And then finally, well, I guess that's actually it. That's all the forces we have that have horizontal components. So we're going to set that equal to 0. And solving for this, you rearrange things however you need to, and you end up that TAF is actually equal to 1.75 kilonewtons. All right, so we found that one, we found that one. Drawing them in over here, we basically found that and that. So we're almost there. We really only have one more member that we need to find the force in, and that member is AB. All right. I'm going to do the free body diagram of the joint at A here. So let me draw that. There's the joint at A, and we're going to look at the forces that act on that joint. So there's one of the forces. That would be TAF. All right, and then we have that force that acts from the support right there that we're going to say is 1.75 kilonewtons. By the way, we know what TAF is from up here, so that's also 1.75 kilonewtons. All right, and then we have this force in member AB. We'll put that up like this. Call it TAB. All right. Stick some coordinate axes on here. This direction is the x direction, and that direction is the y direction. And then we know that the direction of this force is just based on a rise and run both of 4, and that being the case, we've already figured out what that hypotenuse would be. That hypotenuse is about 5.657. Okay, so we're good there. And so really that's the free body diagram we need to work with. We'll do a sum of forces on that free body diagram, and I'm going to do it in the vertical direction there. And there we'll have 1.75 kilonewtons. All right, plus we just need the vertical component of TAB. So what we'll do is we'll take TAB and multiply it by 4 over that hypotenuse length of 0.657, and that should all equal to 0. All right. So if you look at that and do it, you end up with a TAB that is equal to negative 2.475 kilonewtons approximately. All right, and that's the last value that we were looking for. So if we sketch that on here, we have now found the tension, or really the force. It's a compression actually. We know because it came out negative, but we've now found the force in AB, and we already know the force in everything else. So there's the analysis of that truss. If we wanted to, we could go and do a free body diagram of the joint at B and make sure that this analysis actually all came out right, but I'm going to refrain from doing that for now, and if you're interested in that, I'll leave it for you as an exercise.